let's start with our next discussion. Now, there's something very important I would like to cover today. It's called Zookeeper. So, we all talk about Hadoop, HBase, HDFS, and everything, but Zookeeper is actually one of those tools which are very important. It's quite independent in the sense that the way everybody is starting from Pig, Hive, HBase is depending on HDFS. HDFS depends only on Zookeeper. You will see how. So there was this assignment which people get. One more thing, there is an assignment for HBase, and I would like to go through that assignment before it gets too late. Okay, so the assignment I would like to describe that something I always miss. So the assignment is this. It's a subjective assignment. Okay, so yesterday we discussed how to store the the data which was crawled with a relationship, like which page is pointing to which page, and so on. Okay, so we emulated one-to-many relationship in the HBase yesterday in one of the discussion. Today, the assignment for you is, let's say you have to design a simple Gmail like email storage, a email storage which is similar to Gmail. You have to emulate. The only requirement is that it should be able to handle many users. Okay, and it should be able to handle huge data. It should be able to handle many users, and it should be able to handle huge data. And whenever a user comes in, it should be able to give all his emails easily. So you have to design the HBase database such that it's it can handle humongous load, as in it can handle petabytes of data. Okay, so the questions that you need to answer is, what will be the tables in each of these tables, what will be the row keys, and what will be the column families, what will be the columns under each column family for each of the table. Now it's up to you to imagine what all email system you want to provide, but from my side all I want is the normal simple email. I don't want any labeling. I don't want all of this archive, this and that. All I want is that when the user comes in, they should be able to query, they should be able to get their email details. Okay. So, so that is the assignment for today. All right. Now the next question which I want to ask you is, you are writing something called email processor. It could be something like which is creating an email index of the email. Okay, and you are not supposed to modify email. Okay, so the server which contains the emails of the user is single. There is a single machine containing the emails of all the users, and the processors run on multiple machines. So there are multiple machines running the processor who can read the data from, who can read emails from this inbox. And the only problem is that the email processors cannot modify the inbox. Okay, inbox is read only for them. Okay, the other insight is that each email has got a unique identifier. Now question to you is, how would you make sure that no two email processors process the same email? Okay, if one email processor is working on an email, don't process it again. How would you ensure that? Please note that when you are running in multiple threads but on the same machine, or you can say inside a same process, multiple threads can create locks such that one thread does not step on other thread's feet. Okay, so that one thread does not access the same data, so that multiple threads can coordinate. But if there are multiple processes, threads are totally useless. Okay, threads of one process can access the data locked by threads in another process. Okay, so in those cases what we used to do is we used to create a local file to coordinate. But here these email processors are separate machines, so what we need to do is we need to create a central database so that we can write the data in that database and coordinate. And in that database you could actually have something like a bloom filter is actually quite a great concept for the situations like these. Okay, the idea which I wanted to put forward is you need an external service for the coordination between email processors. And when we have been talking about distributed computing, the idea is mainly around this coordination. The idea is mainly around coordination amongst distributed machines. So whether we has so many region servers and HBase is trying to talk to them, or these region servers are coordinating amongst each other. Similarly, data nodes are coordinating amongst themselves. Then primary name node, secondary name node have to coordinate between themselves, and there are many more services that require coordination. Okay, that require coordination. Similarly, for our, say, CloudX Lab right now, we are building our own way so that our users can coordinate well with each other. So basically, whenever there are multiple servers running parallelly in the network and then they need to coordinate amongst themselves, it's very difficult to use the it's very difficult to use the threads or process based locks because these are different machines. Okay, so the general idea used to be let's create a central database, but again this central database could become the bottleneck, because if you have 1,000 processes running parallelly in the cluster and these 1,000 processes require a coordination, a really fast paced environment, this this coordinator, this central database to which all these email processors are talking, all these processes, multi thousands of processes are talking, could become the bottleneck easily. And that's where comes Zookeeper. Zookeeper is a distributed coordination service for distributed applications. It exposes a very simple set of construct or primitives, such as like get and put. Just like a file system, you have a folder structure, you create a folder there so that nobody else can create that folder in that. So similarly, Zookeeper also comes with this nice tree structure so that many processes can create this nodes, trees inside this tree, so that all the processes can happily coordinate with each other. Okay, and it is itself, Zookeeper itself is a distributed, meaning this locking system which looks like a robust single machine, but inside it runs on many machines. We will talk about it today because this is probably the very important idea. Okay, so it is used for synchronization, configuration maintenance, and coordination service that does not suffer from race condition or deadlock. Okay, because every system, if since we are talking about big data need to be handled by many machines, and all these many machines need to coordinate with each other at some point or another. In those cases, Zookeeper will be your go-to guy. Okay, so basically this is what we're going to talk about, the structure of Zookeeper. Now, why are we talking about Zookeeper in detail? Because the structure of Zookeeper is important, because it's going to teach us something very, very, very important. So far we have been having a situation where we were nominating who is master and who is slave. We, being the administrator, we were nominating, okay, this guy is H-base master and rest are the data node. Similarly, this one is a name node, others are data node, and so on. In case of Zookeeper, this is done through election. Just like in a democracy, the master and slave is decided based on elections, and that's why Zookeeper is kind of truly distributed service. Okay, so we will go into the details of Zookeeper today. So uh, Zookeeper's architecture is something which is used by MongoDB and some more. Okay, we will go into the details, and it's very, very important to learn this aspect. All right, to installing Zookeeper, you can extract it and start it, but you don't need to worry about installing on in the case of CloudX Lab. And also it comes pre-installed with Ambari if you are using Ambari for installation. Okay, so I've just run my, okay, so right now what does it say? Zline support is up, and okay, all right. So once you log in into the console here, you type the command called zookeeper dash client, and that way you will be able to see the Zookeeper. Okay, that's how we're going to start. Let me just explain to you what does it mean by Zookeeper. So let's go with the practical first and then theory later. Okay, so the data model is more like a tree structure. Okay, more like a tree structure. Um, it contains basically the nodes, one inside another. The top level is slash. Slash contains one node called Jew here, and inside Jew you have duck, goat, and cow. Okay, so each node is called Z node, as in Z node, and Z node can have children. Children can have data. Okay, every Gnode can have children, every Gnode can have data. Gnode form a hierarchical space. Also, these kind of names are illegal, like this are illegal. And on every node contains the name of the node as well as data. So every node knows whose parent, who is its parent, as well as what is its name and what kind of data it is storing. What data is it storing? So when you change the data on a node, okay, you cannot say append. You can only overwrite the data or change the data. Okay, so that's, in very simple words, that's our data model. Okay, so let's, before jumping into it, going into theory, let me try to show you. Okay, so we are into Zookeeper client. Right now, let's have a look at the way you see the tree structure is just like Unix. You say ls slash, you can see all the subnodes of slash. So right now there are so many nodes. And why there are so many nodes? Because the whole system is actually using Zookeeper. Okay, in every folder, different system is keeping its data. For example, here we have Prezi, we have brokers. Brokers is Kafka brokers. Storm is also keeping its data, and HBase is also keeping its data under HBase unsecure. You can see that you have under HBase, you have all of this information inside Zookeeper. What table locks are enabled? What are the region servers. So you can see inside Zookeeper, everybody keeps its data. Okay, data is in configuration. Right now under region server, there are only these two region servers active right now. There are only two region servers running. And as and when more region servers will run, they will make their entry here. Okay, so you can see ls slash, it shows all the z nodes which are children of slash. Okay, and you can go further into each one like this. Okay, at every node you can say get, it'll show you the data. Right now its data is blank. Okay, and let me go till the last point, zookeeper quota. Okay, let me say get. You can see again its data is blank, so it's okay to have a blank data. All right, let me go into something meaningful. Let's say I say get slash 12 December. I'm saying give me the data of 12 December. So it says its data is initial. All right, I'll talk about all of the details. So I hope you are comfortable with this. So you can see under config is I think it's a Kafka config. It has topics inside it. You can see there are topics inside it. And let's see get. Okay, so there is no information inside it. And let's say I want to check what is the topic containing. Topic is containing this kind of a JSON data. Okay, it says version number this, config this. Okay, so every node has got a name, it has got a children. Okay, like for example these are the various nodes which contain has their names and has got some children. uh, and every node would also optionally would have children. For example, storm has these many children, and under credentials they'll have more details and so on. If you want to see the data what is there inside here, okay, you can see get. All right, that is this data model. Let's go one step further. Now there are different kind of nodes. By default every node is persistent. You make a change to it, it is persisted and kept. Okay, and it remains there until you explicitly delete it. Okay, so the way you create a node is in a very simple way. You can say create slash, slash is the parent, and let's say we want to create a z node called 6 fab. Okay, we want to create 6 fab and we want to put our secret data inside it. Okay, so we have created this node called 6 fab. It's created here. We are using create command, and then here you can see if you want to see the data of 6 fab, we can say get this. Okay, here it's basically expecting us to give the JSON data. Okay, I think it wants us to. Okay, you can see that it has created the data that way. And all right, so we have been able to change the data, get the data, create a node, and we can also create another node inside 6 fab saying Sandeep. Okay, and okay, we can put some information to Sandeep saying he's an instructor. Okay, so we can say okay, So now you can see that we have been able to create this node. Okay, so we have been able to create a node, a lesser node, and then update a node and get the data of the node. All right, so the nodes which we created just now were the nodes that we created just now were basically persistent node. Okay, we can delete these nodes by saying delete 6 fab and something. Okay, okay, so you can see now the data has been deleted. If you are also logged in into a Zookeeper client, you'll be able to see what am I seeing right now. Okay, so this way you can create, delete, check the details, check the children and so on of a particular node inside Zookeeper. All right, now there are some very interesting kind of nodes. You can create an ephemeral node which will be deleted by Zookeeper as soon as the session ends. I'm connected right now. If I create a ephemeral node, it will basically disappear as soon as I get disconnected. Okay, so it cannot have children. Let me just show you first. Okay, so let me create an ephemeral node by saying create minus e 6 fab. Okay, and the node title is Sandeep is online. Okay, sorry, this somehow hates. Okay, so I'll say some data here. Okay, so I've created this Zookeeper node. Okay, right now you can also see there is one node called Sandeep is online. If I exit, so the session has been ended. Okay, that particular session which created that node, okay, has ended. Therefore therefore that node will disappear after some time. Okay, that node will disappear because that session has been ended. So these are ephemeral nodes. Ephemeral node exists as long as your session is active. It cannot have children, not even the ephemeral ones, though it's tied to the client session, but it is visible to everyone. You can create your ephemeral node like this. Okay, so that is, now let's check. It has been deleted. Let me log in again and check 6 fab. All right, it has disappeared after some time. Okay, so this is like creating an attendance system. So every node needs to keep on sending pings to the server so that the server keeps their sessions active, and therefore it will show their presence. Okay, so basically a sequential another kind of node is called sequential node. What is a sequential node? In case of sequential node, Zookeeper creates a sequence number. Okay, the sequence number starts from 0 for every parent. Okay, for every parent the sequence number starts from 0. So, and this whatever when you're creating a sequential node, you just provide the prefix. The sequence number is appended by Zookeeper to the prefix. Okay, for example, I will show you right now how many nodes have been so far created in 6fab. We have created around 3 nodes inside 6fab. Okay, one earlier which we deleted, then we created an ephemeral node. So I think we have created two sub nodes inside 6fab. That means if I create a sequential node inside 6fab, I will get, okay, let me just provide this my prefix. I'm just writing my prefix inside 6fab and some data inside it. So it will automatically create this node. You see, the name of the node is mypref0002. So it started with 0. For 0, it gave to the first node which we created called Sandeep. And then second node 1 was the one which disappeared. And third one is the one, this sequential node. So this sequential running number keeps on going for every node. It's just that it's utilized in while creating a sequential node. So every parent keeps a count of their children by the way of this sequence number. Okay, so based on this, you can always figure out how many children, how many children have been created for a particular node. Okay, so you can see that, and let me also check if we can say get 6 fab. Okay, all right. So this way you can keep a count of what's going on. So this counter keeps on monotonically increasing. If I create another node here, it will increase by 1. Okay, you can see that it has increased by 1. I can, even if I change the prefix, the counter will be in the same way. You can see if I provide empty, then the node of the the name of the z node will be only the number. Okay, so this is another kind of z node called sequential node. All right. Now the architecture. This is very important. I hope everybody is up and running with Zookeeper. Can we see the Zookeeper node on Hue? Yes, you can. Okay, you can see the Zookeeper here. All right, it's showing the current status. Also, what I was about to show you, that also you can see. Okay, right now you can see how many machines are there. 1, 2, 3, 4, 5. After colon is the port number, which is 2181, and before colon is the IP address. So you can see that here there are 5 machines on which Zookeeper is running parallelly. This is a cluster. Okay, one of them is marked as leader, rest are followers. Okay, now this is the folder structure you can see. So generally you can see the Zookeeper from here. No worries. Now let's move on to the next point. All right. Now let me talk about the architect. This is very, very important. So everybody should pay attention to it. This is going to be because it uses a strategy called Paxos algorithm. Okay. So the design of Uzi is based on Paxos algorithm. And if you read the paper, it's actually quite unnecessarily complex. I'll try to make it very, very simple. If you have a question, just let me know. Okay, it's, if you are interested in politics, you will definitely enjoy it. And even people with a little it's basically a very interesting way to look at how systems talk to each other. Okay, it's quite an interesting thing. Okay, so and even if you like the 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 Indian, the Sas Bahu kind of serials, then also you will like the Paxos algorithm. All right, and let me start with it. Okay, all right. So basically, the design of Zookeeper has two modes. One is called standalone, which is just for testing, and it has no high availability. It's not that interesting. That's just for those people who are running virtual machines of any of this would be using Zookeeper in that mode. Okay, but the real thing about Zookeeper is the replicated mode. So in replicated mode, Zookeeper runs on a cluster of machines and we call it ensemble. We give it a nice name called ensemble, this cluster of machines. Cluster of machines is it? Many computers connected over a network, okay? Over a Wi-Fi or whatever you want to use. All right. Now in this, it's quite highly available. Okay. We'll show you how it's highly available and it keeps on running happily as long as majority of the computers are up. Majority means more than half. More than half. Majority, in case there are 3 computers, majority means 2. Okay. In case of 2 computers, majority means 2. In case of 1 computer, majority is 1. In case of 20 computers, majority is 11. Okay, so this ensemble will happily run as long as there is majority of the computers are available. All right, now the architecture. So initially, what you do is you install Zookeeper servers on every machine in your cluster. Okay, so all these machines, let's say here there are 3 machines, A, B, and C. All these 3 machines are running the Zookeeper server. Server as in there is a program called server which runs on 2181 port as you saw just now. And all these 3 machines are running parallelly and talking to each other. They know about all these 3 machines know about every other server running the Zookeeper. Okay, so we turn them on, we switch them on, and then what happens is something interesting. They start talking to each other, and the first thing they do is first thing as we start these machines, we basically configured the server, and then we started the Zookeeper servers on all these 3 machines. And what magically starts happening is they all start communicating to each other. And the first thing they do is all of them first thing they do is do the leader selection. They gossip amongst themselves to select a leader. And basically, whosoever is more responsible. So every machine makes the opinion about other machines based on number of pings responded by the other machines, and then they reconcile the nodes. All machines reconcile the nodes, and then the machine who is designated as the leader wins and becomes the leader, and become the rest become the follower. Okay, now what is the significance of other of being the leader? The leader, all the nodes who want to change something, like we wanted to create a node, they will be redirected to the leader. Okay, followers will only be used when we say get me the list of children or give me the data node, give me a z node data. So for every read request, followers will be used, while all the write requests, the requests that involve change, would be forwarded to the leader. Okay, so as soon as the network is up, the nodes are talking to each other, voting about each other, gossiping amongst each other, and the election happens, and the somebody becomes the leader. And the moment somebody becomes the leader, rest of the followers synchronize their state with the leader. Okay, if the leader fails at any point of time, somebody else will become the leader based on the election. So as soon as a leader fails or leader steps down, election happens and somebody else becomes the leader, and then the same process keeps on happening automatically, and the election takes around 200 milliseconds. If the majority is not available at any point of time, the leader will step down. Okay, if so in this democracy, if lesser than 50% votes if lesser than 50% people, 50% or or lesser people voted, then election is invalid. There is no leader. The whole system will remain read only. There will be no change that can happen in this system. So majority is not available at any point of time. The leader himself, even if there is a leader, he will step down. Okay. Now, once the election is successful and leader has been elected, what happens? Every write request is forwarded to the leader. Leader broadcasts the update to the followers. When the majority have saved or persisted that change, so when we said create node, that change went to majority, went to all the nodes. Okay, which means the most important thing you need to understand, not most, one of the very important thing, that the data on every node is same. Okay, any change you make is propagated to the whole cluster. That means you should always store small data. You should always store small data on Zookeeper cluster. So when majority saves the change, only then the leader says commits, and then client gets a response that your change were successfully written. Okay, majority is again the keyword here, meaning in case of 5 node, when if I have 5 nodes in the cluster, 3 is the majority, and unless 3 nodes successfully write the change, I would not get the response. But luckily, since all the 3 writes are happening in parallel, so it does not take much time. The protocol for achieving the consensus is atomic, like two-phase commit. Okay, so when we are basically reaching to a consensus, like when we are writing the data, it's basically a commit. Now, most other important aspect about Zookeeper is that it saves the data to the disk before the memory. So there were ensemble as in there were bunch of machines. We started on every machine. We started Zookeeper server. So Zookeeper service is nothing but a process listening on a port and talking to other machines. Okay, every machine knows who are the Zookeeper servers available in the network. So Zookeeper servers talk to each other, elected a leader based on who has the latest data and who responded to the pings really, really well. And then they choose a leader, and they synchronize their state with the leader, and then the story starts. And all the write requests, whenever there is a change, delete or update or get or set, the request goes to the leader, while read requests can be served by anybody. All right. So this is a simple architecture. Now, question to all of you: if you have 3 nodes, A, B, and C, A being the leader and A dies. A being the leader and A dies, as in A get disconnected from the network, will somebody become the leader? If you have 3 nodes, A, B, and C, will somebody become a leader if A is no longer available? Yes, that's right, because 2 is still a majority. Okay, so as soon as A is dead, automatically the machines will talk amongst each other, somebody will become the leader. Okay, now either B or C, based on the circumstances, will become the leader. Now question is, what happens when B dies? Let's say C got elected as a leader, and after a while B is also dead. Only C, who is the leader, is left. Will C step down from being the leader or will remain the leader? So okay, let me explain again. So when A was dead, 2 nodes were left, 2 out of 3. is still a majority. 3 divided by 2 is 1.5 and 2 is greater than 1.5. Therefore, 2 is a majority. Therefore, re-election happened. Now, what happened was only one node is left. So, the leader will step down because he's the only one left, or there is no majority in this system. Okay, so we will this is something which took me a while to figure out why is it so. In the first I thought that okay, at least there is one computer available, let's not it should have kept on running and serving the request, but C steps down from being the leader and becomes the follower, and so no one becomes the leader, C will become the follower. Okay, since majority is not available, A is lesser than 1.5, which means lesser than 50% of 3. Therefore, there is no leader. Even if there is a leader in these circumstances, he will step down. Why would it step down? Yes, basically as soon as there is no leader, what happens is there is no write request being served. The whole cluster, the whole zookeeper becomes read only. So any ideas why C has why such kind of behavior? Why do we need majority? Let me go to another. Yeah. Now let's come to the actual answer. I think you will appreciate this part. Let's imagine that there is this data center, there is this network where you have data center 1, data center 2, having total number of 6 nodes, and A being the leader. A is the leader while others are follower. Please note that out of 6 nodes, if 3 nodes are dead, the leader will step down. Even if there are 3 nodes available, it will step down because, I mean, let's understand the reasoning behind it. Let's look at this. There are 2 data centers connected by a wire. One data center containing A, B, and C, and other data center containing D, E, and F. Now, A is the leader and we have, all of them are happy. B, C, D, E, F are all followers and serving all the read requests while the changes are being forwarded to A. Any change comes to D, it's forwarded to A, and so on. So everybody is forwarding the write request to A and they are serving happily the read request. Now, something strange happens here in the network, and the connectivity between data center 1 and data center 2 is dead. So now on one island there is A, B, and C, and on another there is D, E, and F. In these circumstances, what goes on is, now imagine that majority kind of rule was not there. Let's say Zookeeper did not follow majority kind of a rule and elected whosoever gets maximum votes. What could have happened is both the islands would choose their own leaders and will start accepting write request. Any write request is coming to say F is being forwarded to D. So let's imagine that this could have happened. It could have been disastrous. The cable got disconnected between the networks. The data center 1 had chosen its leader called A, and data center 2 had chosen another leader called D. Had majority rule was not there in the architecture, this could have happened, and what would that lead to? 2 leaders in the same country, everyone running the system their own way. And why does it become disastrous when it comes to the information? Imagine that the same tree of information having 2 separate variation. In one there are some more nodes getting added, in another some other deletions are happening. It could have been beyond reconciliation. You won't be able to reconcile. Okay, so the data could have been equivalent to getting corrupted if the majority was not there. Okay, now if that happens in reality, what happens is that the leader A, noting down that okay, only the vote of B and C is available to us, meaning only the 3 nodes are available right now, so leader A would step down, and in the data center 2, nobody will be the leader. All right. So basically, here, all right, let me repeat again quickly. So basically, if there is this kind of scenario, if you and there was no majority kind of a rule. Majority rule says that for election there should be at least 50% people available, for more than 50% people should be available to vote. In this kind of scenario, when the network got disconnected, here there is a three people available to vote, and the other side also there are three people available to vote. In case there was no majority rule, both the data center will choose their leaders, and both the leaders will start operating at the same time, taking the right request, which means the consistency of the data is completely lost. Two leaders means two right requests parallelly being served by two different nodes. Changes are happening to the same thing parallelly by two different nodes, and the whole integrity of the system is gone for a toss. All right. Therefore, it is to ensure that there is always one single leader. There is a rule of majority. No partitioning of the network. This is called partitioning of the network. No partitioning of the network should cause multiple leaders. Therefore, it is because there can be only one majority in any kind of a topology. It's like saying that it's my birthday and I should get the biggest cake. And how can I make sure that I get the biggest cake? By saying that I should get little more than 50%. Similarly, to ensure that there is only one leader, there is only one such network, it is made sure that leader says I need more than 50% majority, and that can be only one, not more than, there cannot be more than one 50% majority in any network topology. Okay, a quick question to all of you. In an ensemble of 10 nodes, it can tolerate a shutdown of how many nodes? So it can only tolerate the shutdown of less than 50, not half. So the answer is 4. All right, there's some more details I need to provide you. So uh, Zookeeper provides you an idea of sessions, just like you have web sessions or TCP/IP sessions. Similarly, Zookeeper also provide you sessions. A client, the client which you use for connecting to Zookeeper servers, has the list of servers in the available, which means the client maintains all the list of IP addresses. It will keep on connecting to each until it's successful. And then it creates a new session. On the server side as well, a new session is created for the client. Okay, and every session has got time period decided by the caller, as in the client. Okay, just like any other web server. Okay, if the server has not received a request within the time period, it might expire the session. If the session get expired, ephemeral nodes are lost. To keep the sessions alive, the client keeps on sending the pings, or called heartbeats. Okay, it's like you keep on refreshing a web page so that it doesn't time out. Okay, similarly the client keep on doing that, but good news is that your program doesn't have to do it. The client library underneath which you're going to do will take care of all the heartbeats. Also, this client library handles the failovers, and sessions are valid on switching to another server. Application can't remain agnostic to the server connection, because while your software, your application is trying to create a node, maybe there is a real action happening. Okay, so you have to be aware that the connection might fail. Okay, so this is a simple connection, as in you create a connection, it's connecting, and then it gets connected, you get an update, and then the connection gets closed. Now, one of the big use case of Zookeeper is if you have millions of clients connected to Zookeeper or to a web server, so on the back end you have a load balance service. Load balance service means a service being run on many machines parallelly, and and there are thousands of clients who would use this service parallelly. Okay, now how to discover which server is up, which server is down? Okay, one way was that all the clients are maintaining a list of servers and keep on pinging to every server and checking which server is up. The right way is to use Zookeeper as the coordinator in the middle. Okay, so every server will create their ephemeral nodes so that their ephemeral nodes will be up as long as the server is up. In case server goes down, their ephemeral node will disappear, and the client will not talk to them. Okay, on one end all the servers will create their ephemeral nodes, and on the other hand the clients will talk to the Zookeeper and get the list of all the ephemeral nodes and will try to connect to only those which are active right now. Okay, so this is, let's say there is a server which connected to Zookeeper and said, hey, create my connection, and then it creates a Z node called duck under servers. Then another server comes up, says create a Z node, ephemeral Z node called cow under servers. And at this point of time, if somebody comes, as in a client comes and says, give me the list of available servers, Zookeeper will say it's duck and cow. But after a point of time, if duck server gets killed, this duck server get killed, so this ephemeral node will disappear. And if that disappears, the Z node will disappear, and which means the list ls/server will only return cow, not the duck. Okay, so this is how the coordination between the discovery of the client server from the client would happen. Okay, so it guarantees that there will be a sequential consistency. Update from any particular client are applied in the order, like the way we were talked about eventual consistency. Here there is a sequential consistency because every change has got a number on it. Atomicity, either Z node change fails or successful, there is no midway. There's a single system image. A client will see the single system image. Okay, the new server will not accept any connection until it has caught up. Okay, so as we told that it provides durability, as in if a change is a change, it is not lost, it is not in the memory, it is in the disk. Timeliness, rather than allowing a client to see very stale data, a server will automatically shut down. Okay, this is a very important part. A server will kind of commit a suicide if it is stale for quite some time. All right, now there are various kinds of operations which we have already seen: create, delete, exist, get cl, and get acl, as in access control list. Access control list is something not too critical for us. Basically, when you have many programs in the network, they might want to access, so we might want to control who is modifying. So if you have many clients, you want to secure one Z node from another, and that's when the access control list come into play. All right, now the update could be multiple or single. Okay, so this is the API for Zookeeper is quite strong. It provides it provides you a way to combine multiple operation into single, just like database transactions. In a database transaction, you can say add a row, update a row, delete a row in a single transaction. All of these changes will happen in a single shot. In the similar way, multi-update makes sure that all the changes like creating a Z node, deleting something else, creating 10 Z nodes, all of this would happen in a single shot. There will be no midway state. All right. So the API which Zookeeper provides you are of two kinds, which is one in Java, other in C. The contributed ones are for Python and REST. So the interesting part is that there are two versions of every function. One synchronous, other asynchronous. What does it mean by synchronous and asynchronous? All right. So there are two ways to talk, two ways to communicate. Okay. Let's say you make a call to me and start discussing things. Okay, saying okay, so how should I say, um, let's say you want to check that the session has been started or not. Okay, or how should I say, let's think about the hotel reception. Okay, so hotel there is a hotel reception. You are staying in a hotel and you are expecting a visitor. There is one way that you keep on calling the reception again and again and asking them that, has my visitor come in? Has a person called Sandeep Giri come in to visit me? Or the hotel receptionist says to you that, hey, I will call you back when somebody named Sandeep Giri comes in. Okay. So in one case, you're continuously pinging. Okay. And in another case, you have just told them they'll call you back. Okay. So in one way, you can say that, or you called the receptionist and said, stay on the phone until Sandeep Giri comes in. That is synchronous call. You are waiting until the work is finished. Okay. In other way, asynchronous, your call finishes quickly and you get a call back when the real event happens. Okay. Every publisher subscriber model is in the same way. So there are these APIs which provide you the callback, and you can also, there's something called watches. So sometimes you want to get notified saying when something happens, just inform me. Like we had triggers and post processors and pre-processors in HBase. So here you want to say that you want to get registered, you want to get watches when something happens on the Z nodes. Okay. So watches are triggered only once, just like in JavaScript. So you will have to uh, basically re-register every time. Okay, you cannot keep getting the updates. You will get only update once, and then in that update logic you can resubscribe. Okay, so when does watch trigger? The watches that are created in the function called exists are triggered when the nodes are created, deleted, or updated. Okay, or get data, the watches of get data gets triggered when the z node, when a z node is deleted or its data get updated. The watches, because the watches are configured when you call a function called get, like exist, get data, or get children. So the watches of get children get invoked or get executed or get called when a node is deleted or any of its children get modified. Okay, so those are called watches. The other thing is ACL, access control list. You can have the permission like authentication and authorization. Okay, the authentication could be based on login password, or it could be based on something called Kerberos, or it could be based on the IP address. All right. So access control list is a function of what kind of authentication you are using, the identity of this of that scheme, and the set of permissions. All right, we have gone through hands-on. We've already tried all of this. You can try by yourself. All right, so the other use cases for Zookeeper are building a reliable configuration service. Okay. Another is building a distributed log service such that not too many process can talk to the same. uh, I mean, not two process have the race conditions. Okay. All right. Now, when not to use Zookeeper, that's a very important part. Do not store big data inside Zookeeper. The total number of copies are equal to the total number of nodes. So, and also all of the data that you store in Znode will be loaded in the RAM. So, Zookeeper is blazingly fast. Zookeeper is extremely reliable, and Zookeeper is sequentially consistent, or you can say heavily consistent. Okay, but the downside is that it keeps data in the RAM and it keeps many copies of the data. So if you are trying to store a 1 gigabyte data and you have 10 number of nodes, it's going to consume overall 10 gigabyte of data and 1 gigabyte of RAM on every machine. Okay, so also, it provides you sequential consistency, not strong consistency. Although here the consistency is going to be great, but it's not as compared to using a singular system like a database or like a file system. So it's not extremely strong consistency. It's basically sequential consistency. So that was Zookeeper.